Welcome, curious minds, to another deep dive. Today, we're embarking on a really fascinating journey into the heart of the online encyclopedia integer sequences, the OEIS. We're picking one sequence that, well, at first glance seems utterly straightforward, yet as we peel back its layers, it reveals this astonishing web of mathematical connections. Our mission today, to explore OEIS A000267. This sequence is simply defined as the integer part of the square root of 4n plus 1. So for this deep dive, we're not just looking at its definition, we're examining its surprising behavior, its various alternative identities, and how it pops up in mathematical contexts you might never expect. It's a brilliant example of how a single string of numbers can offer multiple perspectives and, well, unlock unexpected insights across different mathematical domains. And to guide us through this numerical landscape, we have with us our brilliant expert ready to illuminate the hidden beauty within these numbers.
It's a real pleasure to be here. This sequence, A000267, it's genuinely a prime example of how even what appears to be a very simple definition in number theory can lead to profoundly rich insights and connections that span across various mathematical disciplines. It powerfully illustrates how integer sequences aren't just lists of numbers, but incredibly precise lenses through which you can understand intricate mathematical structures.
Fantastic. Let's jump right in then. When you apply the formula floor, squared 4n plus 1 for n starting at 0, 1, 2, and so on, the terms of the sequence begin. 1, 2, 3, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7, 7. Now, for anyone perhaps new to this notation, the floor function simply means you calculate the value inside the parentheses, and then you round down to the nearest whole number. So if squared 4n plus 1 worked out to, say, 3.7, the floor of that would just be 3. Looking at these initial terms, what's the very first thing that jumps out to you?
Well, what's immediately captivating, as you just read the terms, is that distinct pattern of repetition. You see 3 appearing twice, then 4 twice, followed by 5 appearing 3 times, then 6 3 times, and so on. This isn't just a quirky anomaly, it's a very precise, predictable pattern. Bernard Schott, a contributor to the OEIS page for A000267, he formalizes this. He states that every number k is present consecutively floor 2k plus 3 4 times.
Oh, okay.
This characteristic alone is a powerful hint that there's a much deeper structure here than just a straightforward square root calculation. The repetition acts almost like a mathematical fingerprint, giving us a clue to the sequence's underlying design.
That formula for the repetition is already pretty fascinating. But let's go back to the core definition. Floor, 4n plus 1. What makes that specific expression 4n plus 1 so foundational or, I guess, special in this context? It doesn't seem immediately obvious why that form, as opposed to, say, 2n plus 1 or n plus 1 would be the one.
That's a crucial question. The expression 4n plus 1 is highly significant because it's intimately related to the structure of odd perfect squares. You see, any odd perfect square can always be written in the form 2k plus 1, 2. If you expand that, you get 4k2 plus 4k plus 1.
Okay.
Now, if we let n equals k2 plus k, then 4n plus 1 becomes 4k2 plus k plus 1, which is, well, 4k2 plus 4k plus 1. That's precisely 2pi plus 1, 2.
Well, I see. Correct.
So the square root of 4n plus 1 will be an integer exactly when 4n plus 1 itself is an odd perfect square. The floor function then extracts the integer part, essentially telling us which odd number squared 4n plus 1 is closest to or equal to. It's a very deliberate choice that aligns the sequence with the natural progression of odd numbers being squared.
Okay, here's where it truly becomes intriguing, I think. One of the most captivating aspects of number theory, and indeed the OEIS, is how a single sequence can be described by multiple, seemingly unrelated formulas. For A000267, we have several. For example, Robert A. Stump proposed floor 1 plus 1 deal. My first thought is, how in the world does that expression, with a fraction and square roots in the denominator, how does that possibly produce the same numbers as floor, square n plus 1? It looks like it belongs to an entirely different mathematical universe.
It's a fantastic observation, and it really highlights the hidden elegance of algebraic manipulation. When we encounter an expression like 1 squared n plus 1 squared n, a common technique is to rationalize the denominator.
Right, I remember that term.
Yeah, so for those unfamiliar, this just means we eliminate the square roots from the bottom of the fraction. We do this by multiplying both the numerator and the denominator by something called its conjugate. The conjugate of squared n plus 1 is simply squared n plus 1 plus square n. Now, when you multiply square n tn plus 1 square nt by square n plus 1 plus square tn, It uses that difference of squares identity, a plus b equals a2b2. So the denominator becomes n plus 1n, which, well, it elegantly simplifies to just 1.
Oh, wow.
Which means the entire expression 1 square tn plus 1 squared just simplifies to square tn plus 1 plus square tn.
That's neat.
So Stump's formula is actually equivalent to floor, square tn plus 1, and this connects beautifully to Bruno Berselli's later formula, floor, square tn plus 2, showing how different algebraic forms can reveal the same underlying sequence. It's like finding different maps that lead you to the exact same treasure chest, you know?
That's a genuinely remarkable simplification. It really is like peeling back layers of an onion to find the core. But then we have David W. Wilson's description, which states AN floor NKNZ plus AP. Now, this represents the number of distinct values of floor for positive integers k. That feels like it's from a completely different branch of mathematics, like counting discrete objects rather than calculating square roots. What does this connection tell us?
Indeed, that's a profound shift in perspective. Wilson's formula plunges us straight into the world of combinatorics and number theory, specifically dealing with integer division and divisor functions. Instead of direct calculation, this approach is about counting the unique results you get when you divide n by every positive integer k up to n, and then take the floor of each quotient.
Right.
This tells us that A000267 isn't just about smooth functions like square roots. It also emerges naturally from these discrete counting problems. It implies a deeper connection to how numbers break down through division and how those quotients distribute themselves. And another fascinating alternative comes from Michael Somos, who offers a recursive formula, an_1 plus an_12 for n00.
Recursive. So it depends on earlier terms.
Exactly. This kind of self-referential definition, where a term depends on previous terms, is often a sign of incredibly rich internal structure. It reveals how the sequence can be built step by step. While perhaps not as computationally efficient for finding individual terms as the original floor, square root 4n plus 1, for most computers today, it offers a powerful conceptual pathway to understanding the sequence's growth.
It's incredible how many different lenses we can use to view this single sequence. And it's not just alternative formulas, right? We also see the sequence emerging from different mathematical structures altogether. Philippe Delaham noted that A000267 can be found by reading the diagonals of triangle A094727. For those of us who haven't spent much time staring at triangular arrays of numbers, could you maybe paint a picture for us of what that means?
Absolutely. Imagine triangle A094727 laid out like this. The first row just has 1. The second row has 2, 3. The third row has 3, 4, 5 cuts. The fourth row has 4, 5, 6, 7, and so on. Each row starts with the next integer and then lists consecutive integers up to a certain point. Now, to read it by diagonals, you start at the very top left, which is the 1. Then, for the next diagonal, you pick up the first element of the second row, which is 2.
Right, just the 2.
Then, for the next diagonal, you're gathering elements from this land. You take the second element of the second row, which is 3, and the first element of the third row, which is also 3.
Ah, okay, so you get 3, 3.
Exactly. Then, moving to the next diagonal, you collect the third element of the third row, which is 4, and the second element of the fourth row, which is also 4.
Okay, 4. I see it now. So it would be 1, then 2, then 3, 3, then 4, 4, then 5, 5, 5. This perfectly matches that surprising repetition pattern we saw right at the beginning.
Precisely.
That's brilliant.
Yeah.
So the visual geometric structure of that triangle literally generates the exact repetition we saw in the sequence itself.
That's the idea. This kind of visual or array-based interpretation really helps to solidify the numerical relationships. And it demonstrates how sequences can be deeply embedded within larger, often beautiful mathematical constructs. It's a testament to the elegant patterns that arise when numbers are arranged in specific ways, almost like a natural blueprint for their structure.
It makes you wonder how many other sequences are hiding in plain sight within these elegant geometric arrangements, doesn't it?
Oh, absolutely.
It's genuinely astonishing how A000267 seems to pop up in so many diverse mathematical contexts. It also appears to have a significant historical footprint. I see references to prominent mathematicians like Tom Apostol, Bruce C. Bernst's work on Ramanujan's notebooks, and even S. Ramanujan himself, specifically his question 723. For a sequence defined by something as seemingly straightforward as the integer part of a square root, what's the significance of these deep historical connections? Seems quite profound.
It is profound. The fact that this sequence appears in classic texts by Tom M. Apostle, who was, a towering figure in analytic number theory, and then within Bruce C. Burns' meticulous multi-volume work on Ramanujan's notebooks, and even explicitly in S. Ramanujan's own Question 723, that's incredibly telling.
Ramanujan himself asked about this.
Yes. Ramanujan, truly one of history's greatest mathematical minds, posing a question directly related to this sequence tells us it's far from just a modern computational curiosity. It means A000267, or maybe the underlying mathematical principles that govern it, has a profound, long-standing mathematical lineage. It suggests that it touches upon foundational aspects of number theory that have captivated and challenged brilliant minds for generations. So for you, the learner, this isn't just some modern abstraction. You're engaging with a piece of mathematics that has proven its fundamental significance over time, echoing through, well, the halls of mathematical history.
And perhaps one of the most unexpected revelations in the source material, and a moment that truly made me stop and rethink, is Amiram Eldar's recent contribution from January 2024, a summation. OEIS A000267. This formula involves fundamental constants like pi and the natural logarithm of 2. How does a sequence like this, derived from a simple integer part of a square root, end up connected to something so profound and seemingly unrelated to geometry or logarithms? It feels like finding a secret tunnel between entirely different mathematical dimensions.
This is, without exaggeration, truly remarkable. And it perfectly encapsulates the astonishing interconnectedness of mathematics. It shows how the discrete world of integer sequences can unexpectedly bridge to the continuous world of real numbers and these fundamental mathematical constants that define circles or natural growth.
It's just wow.
Such identities often emerge from advanced areas of mathematics like complex analysis, where numbers extend into a two-dimensional plane and behave in surprisingly symmetric ways, or from the study of infinite series, particularly things like Fourier series, which break down complex functions into simpler, oscillating waves.
Okay, complex analysis, Fourier series, so advanced stuff.
Right. While the OEIS entry doesn't give us the full derivation, the mere existence of such a formula implies a profound underlying structure. It suggests that the terms of AK, when you combine them with alternating signs in an infinite sum, possess specific oscillatory or convergence properties that precisely resolve into these very well-known constants. It's a testament to the hidden beauty and unexpected connections that mathematicians continually uncover. For you, the learner, it highlights that even simple-looking sequences can be gateways to very advanced mathematical concepts, and reveal the deep unity within seemingly disparate branches of the discipline. It's a powerful reminder that the universe of numbers holds many more secrets than we often assume.
So what does this all mean for us? We've taken a deep dive into OEIS A000267, starting from its deceptively simple definition as the integer part of the square root of 4n+1. We journeyed through its distinctive repeating pattern, explored its many equivalent formulas ranging from elegant algebraic simplifications to combinatorial counting. We observed its surprising emergence from triangular arrays, and even traced its deep historical roots back to mathematical giants like Ramanujan. And ultimately, we discovered its astonishing, seemingly impossible connection to fundamental constants like pi and the natural logarithm of 2.
And if we connect this to the bigger picture, A000267 is just a powerful illustration that mathematical objects are rarely isolated entities. A simple number sequence, precisely defined, can be a vital node in a vast, intricate network of mathematical relationships. Understanding these connections not only enriches our grasp of number theory, but also profoundly reveals the underlying unity and elegance of mathematical concepts. It shows us that what might initially seem like a straightforward calculation often hides layers upon layers of unexpected complexity and, frankly, profound beauty.
It's a truly compelling example of how the OEIS can serve as an incredible launchpad for discovery, isn't it? For your own exploration, just consider how a sequence defined by something as straightforward as floor, 4n+1, can be so intimately tied to pi and log 2. What other seemingly simple sequences out there might be harboring such profound hidden connections to the universe's most fundamental constants? The OEIS is absolutely teeming with such wonders, just waiting for curious minds like yours to uncover them.